Hi, my name is David Sankel, and the title of this talk is Don't Constexpr All the Things. So, how did we get here? Well, prior to C++11, the way that we metaprogrammed is we used template metaprogramming. And this is a kind of programming that you can scrap your boilerplate with, but it required somebody special to work on it. You probably had someone on your team who was a metaprogramming expert or a C++ expert that you would use to solve all your metaprogramming tasks. Or maybe it was a person on the team that was next to you. But either way, you really had to get deeply involved into this because template metaprogramming involved programming in such a way that you have to learn a different language, right? It's not like normal C++. It's much closer to a functional programming language, and there are a lot of quirks because this kind of happened by accident. So template metaprogramming is so complicated that almost any use of template metaprogramming warranted a talk at a C++ conference. You can go and talk about how you use metaprogramming to solve X, Y, and Z thing. And that's the status that C++ was in up prior to C++11. Then C++11 came out, and a new library came taking advantage of advanced features. The name of this library is Boost Hana, and this was created by Louis Dion. The basic idea of Boost Hana is that you would actually use normal functions to do your metaprogramming. And it would look like normal functions, but actually there's a lot of complex magic that happens under the hood to make what appears like normal programming, normal code, actually do metaprogramming underneath the hood. Was this easier to read? Absolutely. Easier to write? Well, not really. It was still an expert-only thing, such that if you wanted to be able to do something, or if you did something that was nice with Boost Hana, then that would probably warrant another C++ Now talk to give. And then came Constexpr All the Things. So Ben Dean and Jason Turner came up with this idea to where you can take Constexpr expressions, which were introduced in the C++11, and make a JSON parser out of the thing. And this isn't just making something appear like it's normal code. It actually was kind of normal code. But what it took in order to make this happen, given the limited Constexpr machinery that we had in the language, was absolute heroics. But the key takeaway from this Constexpr All the Things idea is that it doesn't just look like normal code at compile time. It is normal code. So because of the influence of this Constexpr All the Things, we got a slew of papers coming out. The SG7 reflection group, which in a standardization committee, which is now called the metaprogramming group, decided that Constexpr is good. Louis Dion came out with a paper in 2017, which kind of summarized the idea. And it was called Metaprogramming by Design, Not by Accident. In other words, the idea is that we should decide as a language community that we want to design a metaprogramming for our language, rather than have it happen by accident, which is what happened with template metaprogramming. And the key quote that he had from this is, if this can be made to work, this would be the best and most consistent approach to do metaprogramming in C++. So we've had a whole bunch of Constexpr expressions so far. Not only have we added Constexpr to a whole bunch of standard library functions so that they're accessible at compile time, but we've added language features, dynamic allocation, virtual functions, try blocks, non-trivial destructors, std is constant evaluated, const eval functions, const eval variables. We really invested into this idea. But what are we trying to get out of this thing? Why isn't template metaprogramming just fine the way it is, or Boost Hana? What are the goals of this, aside from being by design? Well, one of them is to make metaprogramming just like runtime programming. Not resemble runtime programming, but to really be like runtime programming. And what flows out of this is the second major goal, which is to make metaprogramming accessible, so that you don't need to go to that special engineer on your team or that special engineer on a team which is next to you, that you can actually just pick this up yourself without doing any kind of special learning. So I want you to think, as we go through this talk, of a couple of questions related to this. Are we meeting this criteria? Is there an alternative? Now, we're going to look at some code to help us understand this. This code example has a few different implementations of various functions. The first one there is plus, and note that all these functions have Constexpr put in front of them. And plus just takes a and b and return a plus b, and this is marked as Constexpr. The second function is fast02. And note that the implementation of fast0, what it does is it essentially takes in that vector of ints and makes them all zeros. The name fast is meant to imply that by calling this lower level memset function, it's going to be faster than doing your normal iteration through a loop, potentially. And then our third function here is another implementation of fast0. It's basically the same as the other one, except we have this ifvec.size at the conditional at the beginning of it. Perhaps this is some kind of optimization because we call this function a lot with empty vectors, so we just want to say, hey, if it's an empty case, don't bother calling this studMemset function. Is it okay to mark these things as Constexpr? Well, the first one, yes, of course this is okay. This is just normal code, and you can mark it Constexpr and it'll work just as you expect when you're in Constexpr land. The second function here is going to probably, but not necessarily guaranteed, produce an error. You see, because studMemset, this is a function that isn't a Constexpr function. This is something that is called to some kind of external library. So let's just say that that's not going to work, and most compilers will detect that, although it's not guaranteed, will detect that as being a problem. And then the third version of this function, remember we added that conditional there? Well, this is going to be totally fine. It turns out that by adding this conditional, we're able to say that, yeah, Constexpr, this thing will actually compile. But does it make sense? Well, we have to distinguish between things that can be marked as Constexpr, in other words, that the function will compile and everything works just fine, and functions that are appropriately marked as Constexpr. In this particular example, the first one's appropriately marked as Constexpr, and the two following ones are not appropriately marked as Constexpr. So what exactly are the rules behind when something is appropriately marked Constexpr? Well, an appropriately marked Constexpr function has these properties. It doesn't include gotos, it doesn't include static variable declarations, it doesn't include calls to non-Constexpr functions or inappropriately marked Constexpr functions, it doesn't include calls to naked new, it doesn't throw, and it doesn't include an ASM declaration, and there's over a dozen other rules, and you can look at the standardize for this, and it'll explain all the rules for things to be appropriately marked as Constexpr. Now, one thing I want you to ask yourself is this intuitive? Well, it might be for a compiler designer, but for a user of the language, they probably wouldn't think all these things through. Maybe they would keep a little sheet of paper next to them that explains what all the rules are, so when they're Constexpr metaprogramming, they make sure they don't fall into one of these places where it'll make it not appropriately marked Constexpr. Now, what about types? So it turns out that appropriately marked Constexpr functions must have parameters and result types that are Constexpr friendly. There are some types that aren't Constexpr friendly that you just can't use. So, what is a Constexpr friendly type? Constexpr friendly types have the following properties. It's either one of the simple built-in types, an array of Constexpr friendly types, or a reference to Constexpr friendly type, or it's an aggregate of Constexpr friendly types. That just means essentially like a plain struct. Or it's a class or a union where all the member functions, including constructors and destructors, are appropriately marked Constexpr, and with all its data members Constexpr friendly typed as well. So, with all this, the idea of what's an appropriately marked Constexpr function and what's a Constexpr friendly type really points out, I think, one of the key characteristics that we miss when we talk about Constexpr metaprogramming. The key thing is that Constexpr metaprogramming is a different language to runtime C++ programming. It resembles C++, but it's distinct. You can think of it as a dialect, so that when you are doing Constexpr metaprogramming, you're really having to learn a new language. Another really important point to make about Constexpr programming is that Constexpr code is viral. What do I mean by that? It means that if you take a function and you say, I want to make this Constexpr appropriately marked Constexpr, you have to not just change the function to make sure that it fits the dialect, but if that function calls other functions, and those functions call other functions in beneath, all those functions, all the way down to the very bottom, need to be made to fit this dialect of C++, this Constexpr dialect of C++. This has a pretty huge implication. The implication is that we have a whole bunch of software capital out there. C++, one of its main selling points these days is that it has so much C++ code that you can use. Well, not so when we're talking about Constexpr metaprogramming, because all that code that you use likely doesn't fit the Constexpr dialect of C++. And that kind of stinks. But it actually gets worse. Take a look at this code snippet. Fast0, as we had before, does this memset. We know this doesn't work. This is not appropriately marked as Constexpr. Let's say you take that and modify it, and you do a loop here with a putter I, and you just iterate over the vector and assign it to 0. The first takeaway of this is although this function can be executed at both runtime and at compile time, it's actually going to suffer a performance penalty at runtime because we had to take that code with the efficient memset and do something else with it. The people in the Standardization Committee thought about this, and they came up with this idea of is constant evaluated. And this allows you to write your function in such a way that if you're in Constexpr mode, you can use that dialect of Constexpr C++ and make things a little bit, make something that works, although it would be less efficient if it were runtime. And then if it doesn't match that condition, then you can do the normal std memset, the very fast runtime version, as you see in this example here. So here we go. It's pretty easy. Just if std is constant evaluated, you're in this dialect mode. Otherwise, you can do the runtime C++ mode. Straightforward enough, right? Well, it totally does seem reasonable at first glance. But we do have to go back and revisit the properties of an appropriately marked Constexpr function. So the same is true. It doesn't include gotos. It doesn't include static variable declarations. But additionally, it has this new constraint, which is when this is evaluated as part of a subexpression of a core constant expression, these criteria need to apply, such as doesn't make calls to non-Constexpr functions, it doesn't make calls to make a new, it doesn't throw, and so on and so forth. Well, what is this thing when it is evaluated as part of a subexpression of a core constant expression? Well, it turns out that this particular comment is every bit as complex as it actually sounds. So take this example here. You have a function f, constant I equals g. The question is g evaluated at compile time or is it evaluated at runtime? It turns out that the way that C++ interprets this is what's called a posteriori evaluation. So when you have f and it calls g to produce I here, it will attempt to evaluate g assuming std is constant evaluated is set to true. And if it encounters something illegal, it will instead use a runtime execution with std is constant evaluated set to false. So you as a programmer, you don't really have a good way to know whether or not g is being evaluated at compile time or runtime. It all depends with this a posteriori evaluation. Let's take a look at another example. This one's a little bit hideous. So here we have if Constexpr std is constant evaluated. So if you'll recall, if Constexpr is essentially saying that when you instantiate this, you evaluate this thing, and you will, usually this is used for templates, you will turn on some code and turn off some other code. So it turns out in this case, it will always be the slow version or the fast version. These two things don't interact with each other in a really natural way. An even crazier example taken from David van der Voort's keynote last year at CppNow, which is very good and I highly recommend. This is what it looks like. Here we have a function f that is being called twice. You see on the two lines there when we create p and we create q. When int p is being created, f produces 26. But if you look at when q is created, it ends up creating 36, producing the result of p plus f here. The strange thing about this is constant evaluated. It really gets quite hairy in terms of when that thing becomes true and when that thing becomes false. What my point is that all this complexity needs to be understood in order to generally determine if a function is appropriately marked as Constexpr. It gets worse. So there's more intermingling involved. Unions can have some fields which are Constexpr and some fields that are not Constexpr. Classes can have some Constexpr functions and some non-Constexpr functions. And there's even this idea of Constexpr virtual methods. And the intermingling is really where the complexity gets out of control. So let's take a look at our drawbacks from a high level. Core constant expressions are too difficult to understand. One function implemented in two languages is error-prone. And types with different runtime and compile time capabilities, it's confusing. And then we have dynamic allocation. So here we have
Oh, sorry, I thought I was on mute.
Dude, are you kidding me? How come something happens every time I talk about allocators? But there's even more drawbacks. There are unknown features that are required to make std vector work as expected in that previous example. Allocating data types need to branch on std is constant evaluated when we're talking about allocation. This is error prone, complicated, but ultimately when it comes to the bottom line, this is expensive. So I'm not here to complain about Constexpr metaprogramming. I'm here to talk about a solution. There's a different way we can do this. And the way is called circle metaprogramming. So what is Circle? Circle is a programming language created by Sean Baxter. It's compatible with C++17 and includes some C++20 features. This is something unique in terms of programming. It includes a lot of features, C++20 features such as concepts, but also with C++23 or 26 or things that we have planned and dreams we have down the road, it actually already has, like pattern matching, language variants, reflection, and so on. Now, the way that Sean describes his language, which I think is quite apt, is that it's like C++ went away to train with the League of Shadows and came back 15 years later and became Batman. Now, what Maxime Tertishny says about Circle is that Circle is doing to C++ what C++ did to C. And we always listen to what Maxime says. So let's take a look at some Circle code. This example is quite illustrative. So here we have @meta std_cout hello at compile time. Below that we have in main std_cout hello at runtime. When you compile your test.cpp, you get hello at compile time. When you run the executable, you get hello at runtime. What's happening here? We're outputting text at compile time. We're using the standard library at compile time. That's pretty interesting. What's going on under the hood? Well, let me tell you. Operator, that stream operator, is not annotated with Constexpr or any special token. That operator does not have any special compile time implementation, nor do any of its dependencies. There's no Constexpr going on here. In fact, that stream operator's implementation is vanilla, unchanged vanilla libstd_C++. And that stream operator's core dependencies are being executed from the Linux distribution's libstd_C++.so at compile time. Let's take a look at this next function here. Here we have a function which returns sine of 3 and sine of 5. Okay, this is a normal C++ function. And we call @meta cout f, std end line. And this will output the result of that at compile time. Now note here, f is not marked as Constexpr. F is a plain C++ function. We're actually calling a plain C++ function at compile time. You know, this idea can seem really foreign, but it's actually quite simple. All that we're doing here is running C++ code at compile time, normal C++ code. And that is the basic principle of Circle. Execute normal C++ code at compile time. But of course, just executing code at compile time isn't enough. Like ideally, what we would do is we would take that code which is executed at compile time and be able to influence our runtime behavior. So let's take a look at this example. Here we have f again defined the same way that it was. And below in main, we have Constexpr double val equals at meta f. So at meta f is saying, hey, I would like to execute f at compile time. So when you call at meta f, it produces a double, and then that double is what is set at runtime. And the reason that we use Constexpr here is just to prove to ourselves that this function f is actually called at compile time, even though it's not marked as Constexpr. Let's look at this example. In this example, we have a for loop, but we put the at meta in front of it. And that means that it's going to be executed at compile time. So here, as we run through the loop, we output unrolled loop iteration 0 and then 1 and then all the way until 4. What's going on here is that we have a compile time variable that is being iterated over. If we tried to take this compile time variable and change it in the runtime portion of the code, that'll produce an error. You can't have compile time code be impacted by runtime code. If you wanted to fix that, you'd have to put an at meta in front of it. Then there's this idea of porting. We saw how if you have a double at compile time, it automatically gets synthesized at runtime if you need it. Well, for more complex things like std vector, you can't just automatically take a compile time std vector and make it into a runtime std vector. There's a little bit more work involved there. In this example, we have a std vector, myvec, with a bunch of numbers in it. We call std sort at compile time to sort the vector. But then we want to be able to initialize a vector v with the result of that compile time computation. Like I said, you can't just do that. That automatic porting happens with literals. So how are we going to do it with more complex types? If we wanted to initialize v at runtime, we would do it something like this, where we have a comma-separated list of elements that we'd place in the constructor. What we have to do in Circle is to synthesize this comma-separated list of elements. And this is what that looks like. What we do is call pack non-type, of course we put the at symbol before it, of myvec. And what that does is it creates a parameter pack of ints. You put ... to expand the parameter pack, and then we have everything that we need in order to initialize that std vector of int. There are other injection tools built in to Circle. In this example, we have at expression. What this will do is if you pass any string with a C++ expression in it, is it will convert it, it will synthesize it into that syntax into your C++ program. So here in this example, we have 10 plus 12, it will output 22 when you output it at runtime. In this example, we have something a little bit more complex. We have a meta int j equals 0, and we have this mauto f. What mauto does in this case is mauto is kind of like a return type. And what we're saying is that the return type of f is a synthesized expression. That return statement in f specifies what that synthesized expression should be. So when we look at int x being initialized to f being called with 100, what that will synthesize is 100, which is the I there, times 100, which is that I there, times 0, which is j, that compile time variable. Now that compile time variable got incremented every time f is called, right? So when we have int x equals f of 100, we'll get 100 times 100 times 1. The possibilities here are pretty incredible. Take a look at this snippet. In this case, we have a print function which takes in a string. And again, look at that result type as mauto, which means that it's synthesizing an expression. And this expression, in this case, is cout of at string of s, so that will just take that string, that std string, and convert it into a quoted string, equals at expression of s, so it will take s and interpret that as an expression, and then output end line. Maybe a better way to see how this works is to look at these examples down at the bottom here. So here we have initialize x equal to 12, and we call this special function print of x. And what this will output at runtime is x equals 12. So we use X as a string, and we also use X in a synthesized expression. And then we have print of X times X, and this will output X times X equals 144. You can actually build your own kind of F expressions like they have in Python using just these normal language facilities. It's pretty incredible. The power is amazing. Let's take a look at the circle metaprogramming model. We have an idea of what its capabilities are, but how is this model under the hood? What's really happening here? We'll use some examples to be able to get us to an understanding of that. In this example, start by looking at int I equals 0. This is just a plain global int. Okay, we don't want to do globals. I mean, globals are bad, but it'll help us understand how this works under the hood. And then we have this function f, which returns ++i. Now, when you go to main, and we have three statements here. One is outputting meta of f. The second one outputs meta of f again, and the third one just outputs I. So the first output statement results in 1. And the reason it results in 1 is because it calls f, it pre-increments I, which was started at 0, and it produces 1. And then we do it again, and we get output 2. Now, you may be surprised that when you output I all by itself, it outputs 0. And the reason is because there is a compiler runtime and an application runtime. And these are two different things. So the compiler runtime will have its own global variables and things along those lines. And the runtime, the application runtime, will have its own variables. And they don't interact with each other. What's compile time is compile time, and runtime is runtime. It actually makes a lot of sense, and it makes it very easy to program in and be able to understand what's going on. Now, you might worry about what happens with these compile time globals. Is it just going to like fill your compile time runtime with a whole bunch of stuff? Look at this example. Here we have a classic example of where you have a constructor which does something, and you execute that constructor at static initialization time. So we have this struct C that when it gets instantiated outputs hello world, and we instantiate it right away as a global. And then we have a function f, which just references C, and we call meta of f. And then in main, we call f. Now meta f here, because it is present, this is going to output hello world at compile time. If meta f were not present, it would not output hello world at compile time. How does that work? Well, it turns out that it only statically initializes at compile time that which is ODR used. So in essence, when it comes to globals and your runtime at compile time, you're only paying for what you use, and you're not paying for what you don't use. I don't know. I think that makes a lot of sense. Zooming out a little bit, you can think about circle metaprogramming at 3 different levels. And these different levels have different benefits and drawbacks and different contexts in which they make sense, in which they're used. The first level is that you can run code within the translation unit that you are compiling at compile time. Like we saw when you define a function in there, and then you call that function at compile time. The second level is that you can run standard library code at compile time, like std_cout. It just works. And then the third level is that you can actually run any library code at compile time, even stuff that's outside of the standard library. Now that has some interesting implications. Remember that example from Constexpr All the Things, where we were able to do JSON at compile time? I want you to take a look at what that looks like using circle metaprogramming. Here it is in all of its glory. We include rapid JSON document. This is a well-known JSON library. You initialize the document at compile time, and you call d.parse at compile time. That's it. Think about the gymnastics that had to be gone through with the Constexpr All the Things. And then compare that to these 3 lines in circle. Take a look at this example. Let's say you want to inject a file at compile time and be able to do some compile time stuff with files. Turns out we have a standardization proposal, which is on the way towards standardization, adding a language feature to be able to do this. But with Circle, you don't need a language feature to do this. Here, we're just initializing an IF stream with the path to the file, creating a string out of it, and then we initialize a const char with the contents of that string. That's it. We don't need a language feature. All we're doing is we're executing normal C++ at compile time. There's other examples of this. For example, Constexpr report and Constexpr assert. The idea behind these two things is to be able to output and to be able to do assertions at compile time. We don't need it. You can just use cout and assert. Consider the massive compile speed improvements that you will have if you're doing something really complicated at compile time. Not just because we're interpreting C++ code, we're actually executing C++ code, high performance optimized C++ code at compile time in many cases. This opens the door to a lot of possibilities that are just impossible with Constexpr metaprogramming. Think about the massive software capital that is instantly available at compile time with Circle. You can use it right away. And finally, think about the reduced complexity of all this. This is something that anybody can pick up. Compare that to the Constexpr approach and all those rules that we talked about, and how anybody who's going to be programming in this way is going to have to be aware of all these rules. And let's look back at the Constexpr metaprogramming drawbacks. Requires learning a new language. Constexpr code is viral. Requires understanding core constant expression evaluation, and that's too hard. And you have one function implemented with two dialects of the same language. It's error prone. There's also types with different runtime and compile time capabilities. That's really confusing. We don't know how to make std vector work as expected. And then the dependency on std is constantly evaluated for allocation and things like that. So here's my conclusion. Circle metaprogramming is just like runtime programming, and it's accessible. Constexpr metaprogramming is not. So don't Constexpr all the things. Make it so you don't have to. And I will say, along the lines of what Louis Dion said, if this could be made to work, this would be the best and most consistent approach to do metaprogramming in C++. So, well, I brought this idea to the committee, and, well, you know, I think probably the best way to explain what happened would be to do an enactment of it. Why not?
Disclaimer. What you are about to see is a dramatization of the 2020 Prague ISO C++ meeting. While there was an attempt to capture and summarize the core arguments made there, the actors involved are not representing individual participants nor quoting anyone whatsoever. All nonsense should be blamed entirely on the actors themselves, especially the small one.
Don't Constexpr all the things. Just make it so you don't have to.
This completely and utterly destroys cross-compilation. How can calling an already compiled function at compile time possibly work? Think about it. Let's say I'm cross-compiling to something with a different long size than on my host platform. I then call a function at compile time that takes a long. Well, I need a virtual machine or something like that. This will be impossible. Oh, and by the way, PHP.
Think about it, friends. Arbitrary code execution could possibly go wrong. This is dangerous. Dangerous. Imagine anyone in the world being able to execute code in your compiler. Think of security. My company and clients wouldn't allow it. And I completely agree with what Sarah said. PHP.
I agree with the others. PHP, but also Flash. Compiler plugins will be a disaster. How can anyone do static analysis? They can't.
Arbitrary code execution. I agree. Also, build systems suck. Imagine keeping track of which files arbitrary code pulls in. It makes things more non-deterministic. Dangerous. What will people do with this?
I just want to say that I agree with PHP, Flash, and Danger. I just want to say that I agree with PHP, but not Flash and Danger. What if we allow standard library, but not arbitrary code execution? Danger. PHP.
I'd be less scared, but I'm scared.
Security.
Bottom line is that with this model, we can't prevent people from doing things.
Let's take a poll. We should allow executing arbitrary code execution inside the compiler natively and without a restricted subset like a Constexpr, even including precompiled libraries during compilation. No consensus. Let's take another poll. We should allow executing arbitrary C++ code with using only standard library during compilation. No consensus.
Yeah, that didn't go so well. Heck, this guy over here, he didn't vote in favor of his own proposal. He was so upset about how badly that went. Well, let's take a look at some of the more legitimate concerns that were raised there and see if they can be addressed. The first one, the headliner, is security. Security, security, security. Nobody wants to open up new attack venues to where evil people can come and infiltrate your company, steal their data, and take your company down. But is this actually a legitimate concern? Well, it turns out in a meeting at a cafe afterwards, or just having lunch with a fellow committee member, he actually put it quite succinctly how this concern should be addressed. Let's take a look.
What's the first thing you do when you compile code? You run some tests, right?
The basic idea here is that you run your code after you execute it. Whether you're running unit tests, if you got unit tests, that's great, you're doing great. Or if you don't have unit tests, you run the executable and probably click around a little bit. Either way, this code is getting executed. So if you have code from an untrusted source, don't do that. Don't run it, don't compile it, don't do anything with it. That's the moral of the story here. We're just taking whatever kind of attack venue there was and moving it earlier in the process, which is like 2 seconds earlier most of the time. Now the cross-compilation issues. These are, yes, an absolute corner case and a legitimate concern. There are things to be addressed in this space. And you can address it in a few different ways. One is with porting. If you're running, you want to run on a binary, some kind of third-party binary, well, you may need a port between if you're doing the compilation, because when you compile, you're in the target platform compilation mode. Another way that you could address this is just pull in that actual source code that you wanted to run so the compiler has access to it and can interpret that source code directly, as opposed to running it from a binary, which may be a little bit more complicated. And I'll tell you what, compilers already do this to some extent. But the thing is, don't let this 10% use case get in the way of the 90% use case. If a cross-compiler needs to pull in the source code as opposed to execute something on a binary, it'll be a little bit slower. It won't be slower than Constexpr metaprogramming, but why should we let that stop someone who's actually compiling on the target platform that they have from executing high-performance C++ code? I can't see a reason why. Now, build systems. there are ways to solve this problem too, and you're actually already solving the similar class of problems whenever you package up a binary and distribute it out to wherever it goes. If it depends on any files being there, well, you need to make sure you include that in that package or another package that it depends on, so on and so forth. But the key thing is that you need to state what your dependencies are. And the way that you do this for compile time metaprogramming is you just say, hey, when you compile this CPP file, make sure that you realize that this JSON file over here that I'm reading in is also a dependency. Build systems actually already handle this kind of thing. Yes, there are going to be people who are going to do weird things, but the idea is don't do dumb. Best practices here, whether you're putting an executable together for packaging out, are going to be the same as the best practices that you have when you're doing compilation with this powerful metaprogramming paradigm. So there are degrees of truth to all of the objections that were raised, but the bottom line is that they do not outweigh the good that can be done with circle metaprogramming. This is really an extremely powerful and composable way for you to be able to do metaprograms. It's really a game changer for C++. So someone may say, circle metaprogramming in C++ is dead, or something like that. And to be honest, the air is out of the balloon in Constexpr metaprogramming. It lost its excitement. I mean, if I encounter a problem where I need to solve it with Constexpr metaprogramming, yeah, sure, I'll solve it, but it's going to feel like toil. And the reason it's going to feel like toil is because I know that this can be done in fewer lines of code, much more simply, and much more readable and friendly to your peers' code. So there's that, but on the flip side, Circle is alive and well. And I would encourage all of you listening to this to please, please watch this space. We only talk about one thing that Circle does, and it's a very powerful thing, is that metaprogramming model, but there's so much more in this language. And the fact that it's backwards compatible with C++, I don't know what can happen. It's a pretty exciting thing to be happening right now. Now, if you want to learn more about Circle, go to circlelang.org. This is where you can download the compiler. You can read a bunch of tutorials about how it works. You can get a hold of Sean Baxter, who is the inventor of the language, but he's also very responsive to any kind of email that you might send him. He's been known to just add features to the language upon request. Also, check out this link, wg21.link/p2043r0. This is the paper that underlies this talk that you're hearing right now. So if you want to get the code samples, if you want to go into more depth about any of the things that I mentioned here, that paper is the place to do it. Now, this is the conclusion of this talk. And we'll open up for questions, and I'm very happy to speak to all of you and find out what your questions are about Circle metaprogramming. Thank you. Hey, everybody. So I am ready to take your questions now. So please use the QA button, like at the very bottom there where it has like Q&A. Please put your questions in there. There's currently one question in there. I'm sure you have more than one that you'd like to have answered. So the first question that I see is that supported by Visual Studio and Xcode? I guess the Circle programming language is supported by Visual Studio and Xcode. As far as Visual Studio and Xcode are editors and have the ability to plug in different compilers, different places you can run your compiler executable, I think yes. But I have not experimented with that. I haven't tried it. The second question is, you showed the example with the interpreted string as the X variable. What is about variable scoping? So Matthias, I don't really understand your question. If you want, if you could get unmuted, if we could please have Matthias unmuted, and then maybe you can clarify what you mean by that question.
Yeah, so what I wanted to ask, you showed that where you print out the X and X times X thing, and X was defined in main, and it's not handed over to your print function. So what's the scope of X then? So yeah, so the scope of X is still the same. The scope is in main, but when you call those functions, right, which are actually synthesizing expressions,
You can think of the expression as being formed in the scope where that function is being called, right? So that's why it can talk about X, because it's being formed into that scope.
Okay. So like if I execute a macro.
Yep, exactly. Okay, next question is, oh, actually, Ninad, sorry if I'm pronouncing the name incorrectly, is clarifying that the question is Circle a separate compiler or a kind of preprocessor that can be used with an existing compiler? It's currently a separate compiler. And just to give it like a little background about what it is, it's written on top of LLVM, but not using Clang. So it's like a completely re-implemented compiler built on the LLVM stack, and that's how it works. Next question is, I have no idea how the committee works, but shouldn't it solve the issues of a useful proposal instead of just declining it? Well, I think that part of the committee, it has a responsibility to have what Herb Sutter calls antibodies, which are just a normal negative reaction to like any proposal which comes forward. That's kind of like the default response, just to make sure that the language stays stable and we don't keep on changing it back and forth all the time. And I think that what happened there is that this was a very foreign concept. Like nobody saw this thing coming. I mean, nobody on the committee knew about Circle until basically very shortly before I gave that presentation, because this was developed on the side and we just weren't aware. I think it may take some time for the committee to warm up to it, if they warm up to it at all. It all depends. I think it can be very threatening, this model, for some folks. It's scary. It's different. The next question I see here is, Circle's non-C++ innovation focus seems to be entirely on metaprogramming. Is this trajectory to keep up with C++ 2B, CD features across the board while innovating only on compile time metaprogramming? Or are there other topics where Circle has innovated or wants to innovate? Cough, trivial relocation, cough. I think that the intent of Circle is to produce something which is better than C++. And metaprogramming is one aspect of it, but like I mentioned at the beginning about Circle, it's not the only aspect of it. Way before our pattern matching proposal got so mature, Circle metaprogramming already had pattern matching implemented. And there are many other things that Circle does, and I won't do them justice by trying to list them here. Like, go to the website, download it, try it out. It's innovating in a lot of different areas, and the metaprogramming model is just one of them, but I think it's one of the actually more fantastic things that it's doing. Next question from anonymous attendee. I like that. You mentioned that variables live in either compile time or runtime. Is that the entire story, or is there a recursive set of environments that variables live in? It is the entire story. A variable is either live at compile time or runtime. There is no mix. Well, I guess the closest thing you have to a mix is like a global variable, to where you have it at compile time and at runtime, but they don't cross the boundary. And I think it's just as part of how the model, the Mensa model of this is simple, right? You're either compile time or your runtime, or you're separate compile time and runtime. And that's how it works. Next question. When will all the IDEs that use Libclang for code analysis and completion get support? Well, it's kind of a funny question. I don't manage the schedules for those IDEs for getting support for Circle, but I think that if Circle gets adoption, and I certainly hope that it does, then we're going to see a lot more tooling support coming out. And actually adding tooling support for tooling, or adding tooling support for Circle is not that complicated, because it is C++ 17 plus some additional features. So there's really not that much to be added there, and so on. Okay. Next question from Mark Zerwin. Would it be reasonable to use Circle in production today? And I think that highly depends on what you mean by production. So one thing is that if you compile something in Circle, and like that object code which is produced, that is something that you can link to normal C++ code. So if somebody wanted to do an experimental thing to where they say, hey, I'm going to write this CPP file and this CPP file in Circle, but the rest of my project will be implemented with just normal C++ compiler to try to test out the capabilities, I think that's completely reasonable. Whether you want to put it into production or not, well, there's the question. Is Circle going to be a viable thing? Is Circle still going to be around in 5 years? Nobody knows. Is C++ going to be around in 5 years? Yeah, I mean, I can absolutely guarantee it. So there's a risk involved, but there's a risk benefit because you get the new features, but there's still some uncertainty about Circle's future. Although Sean Baxter is certainly, down to do this, until his death. So we'll see how that goes. The next comment from Stanislaw Dobrowski. Sorry if I mispronounced that. I agree with the PHP criticism on the front end level. The @meta, for example, pun not intended, I find hard/intuitive to read. I understand that this could be considered a POC, but are you fine with this notation as it is? Just a little bit of background on the PHP comment. In the simulation there, we kind of made PHP as kind of like a dismissive thing, but actually in the discussion in the committee, PHP was actually talked about, was not Flash, but PHP was referenced as a positive aspect of this, and that PHP gained so much popularity because metaprogramming was possible for it, and you could do things like this. Now, in terms of this notation, I am certainly not bound to the particular notation, right? What I'm looking for is the power and the essence of the idea. And I'm sure that Sean is very happy to entertain different notational ideas. I haven't really thought that much about it. It made sense to me. It was intuitive enough. There are certainly things that I think that could be improved, but aside from that, it seemed fine. Arthur says, I didn't get the PHP joke. Is it about signaling everything with @? No, it was really just about PHP having this generative capability at compile time, because you kind of generate your web page in a similar way to Circle will generate your translation unit that you're compiling. Next question from Ninad. Can Circle be used for cross-compiling? Does it support targeting Android, iOS, and WebAssembly? What about embedded platforms? I don't have the details on that, but my understanding is that because it's based on the LLVM underneath the hood, it can essentially do cross-compilation there. How effective it will be in terms of has it all been figured out about how to cross-compile and do the interpreted thing and have all that worked out? I don't know to what extent that's been developed, but it's certainly capable of being developed to handle these different situations. Good question. All right, next question. What if you found yourself needing to use a compile time variable during runtime? Can that be done, or would that be a user error of the language? So if you use a compile time variable during runtime, well, you really can't do that because that compile time variable, it only varies during compile time. If you need to use it at runtime, then yes, it'll be synthesized into let's say you have a compile time variable I, and it goes from 0 to 1 to 2 or whatever. When you reference it in some runtime code, it'll put whatever its current value is there, and that will be the runtime execution of it. But you can't modify the compile time variable at runtime. It just, that's not how it works. Next question. As far as I know, Alexandrescu and Dlang also blur the distinction between Constexpr and runtime while letting the compiler choose what to execute during compilation, instead of using @meta to tell the compiler what runs where. Can you comment on the difference between Circle and Dlang and your view on benefits drawbacks? So I can't really speak very much about D. It's not a language that I've explored very much. So unfortunately, I'm not going to be able to answer that question off the cuff because I'd have to learn more about how D's metaprogramming model works. But that's a good question, certainly worthy of investigation. And next question is, does this compose? Can I meta? I don't know the answer to this question. I'm guessing no, but that's certainly interesting question to ask. I don't really know what the use case would be for that, but certainly something that could be explored. Are there any other questions that you all have? Here's one. What do you think should happen if someone tries to @meta OpenGL? I think that what should happen is that it will work. So if you're executing OpenGL, I mean, if you can make your compiler pop up an OpenGL thing, and then you can modify it and hit a button, and then that can impact the generated code. Is there a use case for it? Probably not. But is the power there? Absolutely. And I think the semantics make sense. Now, if you're doing something like, which is, again, like the cross-compilation model, then you get into some weird stuff there. But as far as the use cases that we have for context for metaprogramming, I think they're all handled quite cleanly by Circle. Next question, what about debugging? Say you generate a full struct with metaprogramming. Where would debug info point to, since the actual text defining the struct does not exist on disk? So in terms of debugging, there's always going to be some kind of debugging issue when you're talking about metaprogramming in general. I think that with Circle, you could actually see where things were generated and where they were generated from. And if I recall correctly, Sean Baxter has a talk, or at least I think he's showed it to me, that he did do some kind of like really good debugging support. And actually, it turns out that just being able to do a simple, C out or whatever at compile time aids a lot in debugging. So, and you can also debug as you're running through your compiler, so you can step through the compiler's interpretation of your C++ code at compile time, and that works. And it actually makes debugging quite nice. Next question. I'm still fuzzy on variable scoping. If I pass a string x into some other meta function and it expressions that string, does it get its x or my x? If it's x, did I want that? If my x, how does that work? So if you're doing the injection of expressions, right, it's injected into the expression scope. However, normal variable shadowing rules apply. So if you have a x which you've defined locally, then that x is now in scope and it shadows the one in the enclosing expression. I think that the thing that helped me understand how this works the most was just to try doing a few things in Circle. I did implement that f string function to where you just use Python style f strings where you put in expressions within like curly brackets and that actually helped solidify it all. So I'd recommend doing that. And I don't know, maybe next year or something like that, we could do some kind of a Circle workshop where I think that getting hands-on practice with this will help a lot. Next question. Does it work across translation units? Can you call @meta_f in a.cpp and implement f in b.cpp? And the answer to that question is yes, you can. When you invoke the compiler, if you have any kind of symbols that need to be resolved at compile time, you need to make sure that in that invocation, the compiler, you tell the compiler where those symbols are. So it works in the same way as to if you want to call like rapidjson.so code, which is compiled in some other translation unit. You just need to make sure you point the compiler to that SO for rapidjson, and then any symbols can be resolved to that location. Next question. I think the second straw poll and the attempt to find some path from now to full-fledged Circle makes sense. Can you propose some path with baby steps that can ease this into the standard? I could. I'm not really sure. The committee's reaction to this idea was actually quite surprising to me. I did not expect there to be such universal distaste of this. It could be that those opinions could change, once more time is spent, thinking about things. It could be that they're entrenched. I don't really know. Probably the next time we have a face-to-face standardization meeting, it makes sense to bring this up again and get what people's thoughts are. But if the consensus is that bad, usually it's kind of insurmountable to change it around. So I'm not too optimistic about this being able to get into the standard, unfortunately. I'd love to have my mind changed. I really would. Any other questions? Okay, so no more questions. I think that I'll be around in the little thing where you're the little character walking around. So if anybody has any questions, feel free to reach out to me. And I'm glad you all showed up, and I hope you enjoyed the talk. And I will see you all later. Have a good one.